The question is to analyze function concavity and inflection points. We are given a function that is a product of two parts, a linear expression and a cube root involving a power of x. Our goal is to understand how the graph of this function bends, whether it curves upward or downward, and at which point it changes direction, known as inflection points. First, let's think about where this function is defined. Since cube roots can be taken for any real number, positive, negative, or zero, and we are multiplying by a linear expression, the function is defined for all real values of x. In other words, we can plug in any x value we want. Next step is to rewriting the function. To make it easier to work with, especially for taking derivatives, we'll rewrite the function in terms of exponents instead of roots. The cube root of x raised to the fourth power is the same as x raised to the 4/3 power. So when we multiply x plus 2 by x to the 4/3, we get two terms. The first is x raised to the 7/3 power, and the second is 2 times x raised to the 4/3 power. That gives us a simplified version of the function with two power terms. Next step is to first derivative. Now we find the first derivative by applying the power rule to each term. The derivative of x to the 7/3 is 7 divided by 3 times x raised to the power of 4/3. The derivative of 2 times x to the 4/3 is 8 divided by 3 times x raised to the power of 1/3. So the first derivative consists of those two terms added together. Next step is to second derivative. Now we'll take the derivative of that expression to get the second derivative. The derivative of the first term, which is 7 over 3 times x to the 4/3, becomes 28 over 9 times x to the 1/3. The derivative of the second term, which is 8 over 3 times x to the 1/3, becomes 8 over 9 times x raised to the negative 2/3. So the second derivative is the sum of those two terms, 28 over 9 times x to the 1/3, plus 8 over 9 times x to the negative 2/3. Next step is to factoring and analyzing the second derivative. Now let's factor the second derivative so we can more easily tell when it changes sign. We factor out 4 over 9 times x raised to the negative 2/3 for both terms. What remains inside the parentheses is 7x plus 2. So the second derivative is 4 over 9 times x to the negative 2/3 multiplied by the quantity 7x plus 2. This expression helps us identify where the second derivative is positive or negative, and therefore where the function is concave up or concave down. Next step is to identifying key x values. Let's figure out the values of x that might make the concavity change. We set 7x plus 2 equal to 0 and solve for x. That gives us x equals negative 2 divided by 7. This is a point where the second derivative becomes 0, which is often an inflection point. We also look closely at x equals 0. At this point, the expression involving x to the negative 2/3 has a sharp behavior change. So we'll treat it as a boundary and examine what happens on either side. So now we divide the number line into three intervals. Less than negative 2/7, between negative 2/7 and 0, and greater than 0. Next step is to sign analysis for concavity. Let's test the sign of the second derivative in each interval. First, for values of x less than negative 2/7. The term 7x plus 2 is negative, and the x to the negative 2/3 factor is always positive. So the product is negative. That means the function is concave downward in this region. Next, for values of x between negative 2/7 and 0, 7x plus 2 is now positive, and the x to the negative 2/3 term is still positive. So the second derivative is positive. That means the graph is concave upward in this interval. Lastly, for values of x greater than 0, both parts of the second derivative are positive again, so the function remains concave upward. Next step is to finding the inflection point. We now look for inflection points, points where the function changes concavity. At x equals negative 2/7, the second derivative switches from negative to positive, which confirms that this is indeed an inflection point. Let's find the y-coordinate by plugging negative 2 over 7 into the original function. That gives us the value of the function at x equals negative 2/7 as the quantity negative 2 over 7 plus 2 times the cube root of negative 2 over 7 raised to the 4th power. That simplifies to 12 over 7 times the cube root of 16 over 2,401. We don't need the exact decimal, but that gives us the coordinates of the inflection point. Now, regarding x equals 0, although the expression behaves differently around 0, the second derivative is positive on both sides. So there is no sign change, and therefore, no inflection point at 0. The function is concave downward when x is less than negative 2 over 7. It is concave upward when x is greater than negative 2 over 7. There is a single inflection point at x equals negative 2 over 7, with the corresponding y-coordinate being 12 over 7, times the cube root of 16 over 2,401. When solving problems involving concavity, Rewrite radical expressions using exponents for easier differentiation. Factor the second derivative whenever possible to help analyze its sign. Pay close attention to where the second derivative equals 0 and how its sign changes around those points. An inflection point only exists if the concavity truly changes. It's not enough for the second derivative to simply equal 0. That's it for this question. This video is based on our math tutoring blog and class recordings. Hope you enjoyed it. Please subscribe to our channel. If you're looking for tutoring on final exam level questions, check out my YouTube channel at MathTutor8285. You'll find helpful explanations and strategies to ace your exams.